And also we discuss high yield topics of the all subjects, and also we cover most expected topic for the university exams. In Oracle, we provide live classes for the elevated learning of the student, where knowledge meet interaction. In Oracle also we have recorded session. Recorded session are for the students, so the student will have the access of the class anytime, anywhere. Notes are being provided that are basically CBME, having CBME based question answers, MCQ and full zone for self-assessment. MCQs are there from beginner level to expert level, which contains standard multiple choice questions. In today's class, we're going to do long and short questions. In long questions, we are going to know about that how carbon dioxide is transported in blood from tissue to alveoli. Then we're going to know about the regulation of the respiratory center. Then we're going to know about the pulmonary function test. We're going to discuss about spirometry, pulmonary volume, pulmonary capacities, and time vital capacity. And in last, we're going to know about the flow volume. Then also we're going to discuss that how oxygen is transported to tissues in blood. We provide subscription plan. Subscription plan is basically starting from basic to premium to mentorship plan. Mentorship plan is of 12 months and it's cost around 50,000. We provide services like pre-recorded classes, live class, live doubt clarification, one-to-one personalized guidance, notes, quick revision, examination video. Now let's start with today's class. Also, the student can book a slot for personalized counseling session so that they will get direct interaction with the counselor. So let's start with today's class. So we are today having the respiratory system class 2. First, we're going to know about the PFT. PFT means pulmonary function tests, and we're going to name all those tests which are related to pulmonary function tests. So in spirometry, we have SVC manual, FVC manual, maximum voluntary ventilation, maximum respiratory pressure. In absolute lung volume as a measurements, we do about the body plethysmography, nitrogen burst out method, then helium dilution method, then test for exchange cases like diffusion lung capacity of carbon monoxide, and test for cardio pulmonary interaction. We have 6-minute walk test and cardiopulmonary exercise testing. Okay, now we're going to start with the spirometry. Okay, so basically we know that pulmonary function tests are very useful in assessing the functional status of the spirometry system, both in physiological and pathological condition. So basically, what is spirometry? So spirometry is basically made up of a metal and it contains 2 chambers. If we talk about the spirometry that we do manually, but in the picture you can easily see that this spirometry is basically is automatic, okay, in which the person will inhale the gases and directly the readings will get with the help of the monitor. Okay, so basically spirometry is used only for a single breath, and repeated cycle of respiration cannot be recorded by using this instrument because of carbon dioxide accumulates in the spirometry, or an oxygen or fresh air cannot be provided. Okay, so the spirogram is basically the graphical record of lung volume and capacities, and upward deflection of the spirogram denotes the respiratory and downward curves indicate the expiration. Okay, so to determine the lung volume and capacity, 4 levels are there that can be noted in the spirogram, like normal and expiratory level, then normal and inspiratory level, then maximum expiratory level, then maximum inspiratory level. Okay, so in the picture that we can see is basically a computerized spirometry, and it is a solid state electronic equipment that we can see, and it does not contain any kind of drug or water chamber. The subjects has to respire through a sophisticated transducer that we can see, which is connected to the instrument with the help of this cable and wire. Okay, now various disadvantage of this spirometry is also there. These disadvantages like so by using simple spirometer or respirometer or computerized spirometer, not all the lung volume and lung capacities can be measured. Okay, so volume which cannot be measured by spirometry is the RV. RV means residual volume cannot measured. And this is the most important MCQ question also, that which lung volume is there which cannot be measured using spirometry. Okay. Okay, now capacities which include residual volume also cannot be measured. Okay, and capacities that include residual volume are functional residual capacity and total lung capacity. So they cannot be measured by using spiro. Okay, now volume and capacities which cannot be measured by spirometers are measured by a different method, and the name of that method is nitrogen washed out technique or helium dilution technique, or by body plethysmograph. Okay, so these are the technique by using that we can measure the residual volume, but using spirometry we cannot measure the residual volume, right? Now next we have the pulmonary function. So in pulmonary function, already we have learned about the various things that why pulmonary function is very, very important. So now in pulmonary function test, we're going to learn about the pulmonary volume or lung volume. Okay, so first we're going to talk about the static lung volume. So static lung volumes are volumes of air breathed by an individual. In each of these volume represent the volume of air present in the lungs under a specified static condition. Okay, and what are those volumes? We have volumes like tidal volume, then inspiratory reserve volume, then expiratory reserve volume, then residual volume. Okay, so one by one, we're going to understand each of them. Okay, so first we have tidal volume. So what is tidal volume? Tidal volume is the volume of air that we breathe in and breathe out in a single normal quiet breathing. Okay, so this is need to remember that it is measured in single normal quiet breathing. Okay, and tidal volume signifies the normal depth of breathing, and talking about the normal value, so it is 500 ml or 0.5 liter, right? Now, next we have IRV. IRV means inspiratory reserve volume. So, as the name indicates, inspiratory reserve volume. So, this is the additional volume of air that can be measured or by the inspired forcefully after the end of normal inspiration. Okay. So, again, I'm repeating that it is an additional volume of air that can be inspired. Means during normal quiet breathing, we inspire and expire. But whenever we put any kind of efforts for inspiration, so that is inspiratory reserve volume. Okay. And it is 3300 ml or 3.3 liter. Okay. Now, next we have expiratory reserve volume. What is expiratory reserve volume? It is again the additional volume of air that can be expired out forcefully. Means during quiet breathing, what we are doing, we are inspiring and expiring. But if we are expiring with the very forceful efforts, like this, so it will be expiratory reserve volume, and its normal range is 1000 ml. Okay, or 1 liter. Fine. Next, we have residual volume. So, what is residual volume? This is the volume of air remaining in the lungs even after forced expiration. Okay, if I'm expiring like forcefully. like this. But still, some amount of air is present inside the lung. So that is the residual volume. Okay. So normally the lungs cannot be emptied completely even by the forceful expiration. So some quantity of air always remain in the lungs even if I am expiring very forcefully. Okay. So what is residual volume? It is 1200 ml. Fine. Next, we have the pulmonary capacities or lung capacities. Okay, so when we talk about the lung capacities, so in static lung capacities, uh, we have inspiratory capacity, then vital capacity, then functional residual capacity, then total lung capacity. Now, one by one, we're going to discuss about each of them. Okay. So first we have inspiratory capacity. So what is the inspiratory capacity? This is the maximum volume of air that can be inspired after normal expiration. Okay. And it includes tidal volume and inspiratory reserve volume. Okay. So what is the formula for inspiratory capacity? It can be determined by using tidal volume plus inspiratory reserve volume. So we know tidal volume is 500 and inspiratory reserve volume is 3300. So we get 3800 ml. Okay. Now, next we have vital capacity. So, what is vital capacity? This is again the maximum volume of air that can be expelled out like this, expelled out forcefully even after a deep inspiration. Like if I'm inspiring like very deeply and again I'm expiring forcefully like this. So, this is vital capacity. Okay. So, it includes IRV plus TV tidal volume plus expiratory reservoir. And again, we get the 4800 by adding all of this. Okay. Now, next we have the functional residual capacity. Okay. So, what is functional residual capacity? This is the volume of air that is remaining in lungs after normal expiration. And again, we have the formula to determine that is ERV plus RV. So, we get 2200 by adding because ERV is 1000 and RV residual volume is 1200. Okay. Now, finally, we have total lung capacity. As we can see in the chart also, this is we have inspiratory capacity, vital capacity, functional residual capacity, and total. Total, this is we have total lung capacity. Okay. So, total lung capacity means the volume of air that is present in lungs after a deep inspiration. Like I'm inspiring, expiring. But if I forcefully inspire with all my efforts, and that amount or that volume of air that is present inside the lungs, that is total lung capacity. So for total lung capacity, again, we have a formula that is IRV plus TV plus ERV plus RV. And in total, we get it around 6000 ml or 6 liter. Fine. Now, next we have the time vital capacity, or it is known as forced expiratory volume. So this is the fraction of vital capacity that is expired during the first second, during the second, or during the third second of forced expiration. Okay. So for determining the time vital capacity, we have 3 seconds. Okay. So basically this forced expiratory volume or tight volume vital capacity is the volume of air that can be expired forcefully. I'm inspiring that I'm expiring forcefully in a given unit of time after a deep inspiration. Okay. And it is also known as we have discussed, the tide vital capacity is also known as force vital capacity. So it is a dynamic lung volume. Okay. So we determine it in a FV1, FEV2, and FEV3. Okay. So this is the volume of air expired forcefully in 1 second, volume of air expired forcefully in 2 seconds, volume of air expired forcefully in 3 seconds. Okay. And if you talk about the normal value, so FEV1 is the 83% of total vital capacity, FEV2 is 93% of total vital capacity, and FEV is 97% of total vital capacity. And after this 3 seconds, it will be 100%. After 3 seconds, it will be 100% of total vital capacity. Okay, so vital capacity may be almost normal in some of the respiratory disease, and FEV has great diagnostic value as it decreases significantly in some respiratory disease. It is very much decreased in obstructive disease like asthma and emphysema, and it is slightly reduced in some restricted disease like fibrosis of lungs. Fine. Now, next we have flow volume loop. Okay, so what is this flow volume loop? It is a plot of inspiratory and expiratory. Okay, so on the y-axis, we can see this is the plot of inspiratory and expiratory against volume on the x-axis. So here on x-axis, we have volume. Okay, so these are we are plotting during the performance of maximally forced inspiratory and expiratory maneuvers. Okay. Now, what is the technique for flow volume? Okay, flow volume loop. So, doctor may use a flow volume loop test when diagnosing the disease like COPD. And this test measured that how much air flows when someone can produce breathing, giving their lungs volume. Okay, so a flow volume loop test required people to breathe through a mouthpiece into a machine that measures airflow, right? Now, if we talk about the restrictive and obstructive diseases, okay, so restrictive respiratory diseases is the abnormal respiratory condition that is characterized by difficulty in inspiration, and obstructive respiratory diseases is the normal respiratory condition that is characterized by difficulty in expiration, right? So, in obstructive disease, the loop shift towards the left and the volume are greater than the normal, and FV1 decreases more than the FVC, and there will be lower ratio of FPV1 to FVC, right? Then in restrictive lung diseases, the loop will get shift towards the right and volume will be lesser than the normal, and FEV1 and FVC decreases in the proportion, and the normal or elevated FPV1 upon FVC can be seen in this condition, right? Now, next we have that how oxygen get transported in blood. So we know that blood serves to transport the respiratory gases, and oxygen, which is very essential for the cells, is transported from alveoli of lungs to the cell, and carbon dioxide, which is a waste product in cells, is transported from cells to alveoli of lungs, right? Now, we're going to first understand that how there may be transportation of oxygen occurs, okay? So, oxygen is transported from alveoli of lungs to the cells by blood in two forms. And what are those forms? Like as simple physical solution, So that is approximately 3%. And in combination with HP, that is approximately 97%. Okay, so one by one we're going to discuss. So first, if we talk about the simple physical solution, that is approximately 3%. So oxygen get dissolved in water of plasma and get transported in the physical, right? So the amount of oxygen that get transported in this way is very negligible, or it is very less actually. Okay, so it is the 0.3 ml per 100 ml of plasma, and it forms only 3% of total oxygen in blood, and it is because of poor solubility of oxygen in water content of plasma, right? So still the transportation of oxygen in this form become important during the condition, like whenever the person is doing muscular exercise to meet the excess demand of oxygen by the tissue, right? Now next we have in combination in HB. So oxygen combines with HB in blood and get transported as oxyhemoglobin. And the transport of oxygen in this form is very, very important, because maximum means 97% of oxygen is transported by this method. Okay, then if we talk about the oxygenation of hemoglobin. So when oxygen combines with hemoglobin as a physical combination, it is not only oxygenation and oxidation. This is a type of combination of oxygen with hemoglobin has got many advantages, like oxygen can be readily released from hemoglobin whenever it is needed. Okay, and hemoglobin accepts oxygen readily whenever the partial pressure of oxygen in the blood is low. Okay, so hemoglobin gives out oxygen whenever the partial pressure of oxygen in the blood is less, and also the oxygen get combines with the iron in heme part of hemoglobin, and each molecule of hemoglobin has 4 atoms of iron. That needs to remember. It is an important question. MCQ question. Okay. Then iron of the hemoglobin is present in the ferrous form, and each iron atom combines with 1 molecule of oxygen. So after combination, iron remains in the ferrous form only, and that is why the combination of oxygen with the hemoglobin is known as oxidation, not or it is known as oxygenation, not oxidation. Okay. Now next we're going to know about the this ODC. ODC means oxygen dissociation curve. Okay, so oxygen dissociation curve is the curve that demonstrates the relationship between partial pressure of oxygen and the percentage saturation of hemoglobin with oxygen. Okay, so this is, we have partial pressure of oxygen, and here we have percentage saturation, of HB. Right? So this is basically the sigmoid form. It is like this, the normal, and this is showing the shift to left, shift to right, and this is we have shift to left. Right. So normally in the blood, the hemoglobin is saturated with oxygen only up to 95%, and saturation of hemoglobin with oxygen depend upon the partial pressure of oxygen. And whenever the partial pressure of oxygen is more, hemoglobin accepts oxygen, and whenever the partial pressure of oxygen is less, hemoglobin releases oxygen. Okay. So in this, very important factors are there. Like first we have shift to right. This is shift to right, and this is shift to left. Right? Shift to right and shift to left. Okay. So we're going to discuss about the factor affecting this dissociation curve. First, we have shift to right. So whenever the curve is shifting towards right, means it's clearly indicating that there is dissociation of oxygen from hemoglobin, and it can shift due to whenever there is decreased partial pressure of oxygen, whenever there is increase in hydrogen ion concentration, whenever there is increase in body temperature, or whenever there is excess of 2,3 dpg present. Okay, then we have shift to left. And this shift to left occurs whenever there is increase in partial pressure of oxygen, decrease in hydrogen ion concentration, decrease in CO2. Okay, so these are the reasons for the shift to right and for the shift to left, right? Now, next we have that how CO2 get transported in blood from tissues to alveoli. Okay, so carbon dioxide is transported from the cells to alveoli of lungs by the blood in the four form, and those forms are as dissolved form, that is 7%, as carbonic acid, that is almost negligible, then as bicarbonate, that is 63%, and as amino compound, that is 30%. So one by one, we're going to discuss all these forms. First, we have as dissolved form. Okay. So we know that carbon dioxide diffuses into blood and dissolving the fluid of plasma due to forming a simple solution. Okay. So only about 3 ml per 100 ml of plasma of carbon dioxide is transported as dissolved state, and it is approximately 7% of total carbon dioxide present in the blood, right? Now, next we have the second form, that is carbonic acid, and it is considered to be the negligible oil. Okay, so part of dissolved carbon dioxide in plasma combined with water to form the carbonic acid, and the transport of carbon dioxide in this form is very less, right? Now, next we have as bicarbonate. So approximately 63% is transported as bicarbonate, and from plasma, carbon dioxide enters the RBCs, and in RBC, carbon dioxide combined with water to form carbonic acid. Okay. And whenever this carbonic acid forms, so this reaction inside RBCs are very rapid because of the formation of a enzyme, that is carbonic anhydrase. Okay. Now, this carbonic anhydrase is present only inside the RBCs, not in the plasma. That is why carbonic acid formation is at least 200 to 300 times more that as compared to the plasma. Okay. Now, this carbonic acid is a very unstable compound, and it can dissociate very immediately into bicarbonate and hydrogen ion. Right? So, concentration of this bicarbonate ion in the cell increases more and more, and due to high concentration, bicarbonate ion diffuse through the cell membrane into plasma. Right? Now last we have as carb-amino compound. Okay, so approximately total 30% of CO2 is transported as carb-amino compound, and carbon dioxide is transported in blood in combination with hemoglobin and plasma protein, and carbon dioxide combined with hemoglobin to form the carb-amino hemoglobin or carb hemoglobin. So the reaction will be this. Okay, and it combined with plasma protein to form carb-amino proteins, and carb-amino hemoglobin and carb-amino protein are together known as carb-amino compounds. Fine. So finally, next we have the regulation of the respiratory center. So we know that this respiration is a reflex process, and it can be controlled voluntarily for a short period of time, like for about 40 seconds. And by practicing, the breath can be withheld for a long period, and at the end of the period, the person is forced to breathe. Okay, so respiration is subjected to variation even under the normal physiological condition. For example, if we talk about the emotion condition or during exercise, the rate and force of breathing get increased. Okay, now, but the altered pattern of respiration is brought back to normal within a short period of time by some regulatory mechanism in the body. And the mechanism, we have two types. The first, we have nervous or the neural mechanism, and second, we have chemical. Okay, so for nervous mechanism, we have respiratory center. First, we're going to know about the nervous mechanism. We have respiratory center, like medullary center, we have DRG and the role of VRG. DRG means dorsal respiratory center and VRG means ventral respiratory center. And second, we have Pontine center. And for Pontine center, also we have two, that is agonistic and pneumotoxic. Now, one by one, we're going to know the function of all these centers. So first, we have dorsal respiratory group of neurons, means this DRG. So this center is present. Basically, this is present in the nucleus of tractus solitarius, which is present in the upper part of medulla oblongata. Because we are talking about the medullary center, so obviously the location will be medulla, right? So this is present in the upper part of the medulla oblongata, and in this DRG we have inspiratory neuron. So that's why it is known as inspiratory center. Right. Now, what is the function of this inspiratory center? So as the name suggests, inspiratory. So all the neurons of this dorsal respiratory group are in, basically they are having inspiratory neurons, and they generate the inspiratory ramp by virtue of their autorhythmic property. So they are responsible for basic rhythm of respiration. Right. Now, next we have the another group, that is VRG. VRG means ventral respiratory group of neuron. That is present again in medulla, and they are having nucleus, that is nucleus ambiguous and nucleus atrocambiguous. And these two nuclei are situated in the medulla oblongata, anterior and lateral to the nucleus of tractus solitarius. Now, talking about their function, so this VRG is inactive during quiet breathing. Okay, but it is also having this expiratory neurons. Okay, but this is inactive during quiet breathing when we are like expiring very normally, because expiration is always a passive process. Okay, but it also become active process whenever we expire forcefully, right? So during forced breathing, these neuron or this center become active. Okay, so both inspiratory and expiratory muscles will be worked there. Okay, so this center is also always get active during the forceful expiration. Otherwise, it remain inactive. Right. Now, next we have the Pontine center. So this Pontine center has two parts, that is aponistic and pneumotaxic. So in aponistic center is situated in nuclei reticular formation of lower pons. Okay, so as the name suggests, pontine means this is all both are present in pons. So this is present in lower pons. Okay, now what is the function? So function is to increase the depth of inspiration. Increase the depth of inspiration. Okay, now this pneumotaxic center is situated in this dorsal lateral part of reticular formation and upper pons. And the primary function of this pneumotaxic center is to control the medullary respiratory center, particularly the dorsal group of neurons. Okay, and it acts through aponestic center, and this pneumotaxic center inhibits the aponestic center so that the dorsal group's neurons are inhibited. So because of this, the inspiration stops and expiration start. So this is also known as the switching off center. Okay. Now, finally, we have the chemical regulation. So for chemical regulation, we're going to understand this chemical regulation by drawing a flow chart. So whenever there is decreased ventilation, so decreased ventilation means there will be decrease in partial pressure of oxygen, increase in hydrogen ion concentration in blood, and increase in partial pressure of CO2 in blood. Okay, so whenever there is decrease in partial pressure of oxygen, so there will be stimulation of some receptors. And as we are talking about the chemical regulation, so obviously there will be stimulation of chemical receptors. So the chemical receptors are chemoreceptors. Okay, so there will be stimulation of peripheral chemoreceptors. And these peripheral chemoreceptors will generate impulse, and those impulse will travel through hearing nerve and aortic nerve. Nerve and aortic nerve. Okay, and whenever there is increase in partial pressure of oxygen, so what CO2 will do? CO2 will diffuse into the CSF. Okay, so the CO2 diffuse into CSF. And whenever CO2 diffuse, it will form the hydrogen ion. Okay, how it will form? Like CO2 get diffused into CSF, where it combined with H2O, there will be formation of carbonic acid. And as this carbonic acid is a very unstable compound, it will dissociate into bicarbonate and hydrogen ion. So in this form, there will be formation of hydrogen ion. Okay, so there will be formation of hydrogen ion. Right? Now, there will be there will be formation of hydrogen ion, and hydrogen ion stimulates the central chemoreceptors. Okay, so from chemoreceptors, from the central chemoreceptor, the excitatory impulse are sent to dorsal respiratory group of neuron, and they will be increasing the ventilation. Okay, so it will lead to stimulation of central chemoreceptors. Okay, so both from here and from here, there will be stimulation of DRG, and it will lead to increased ventilation. Okay, so always remember that the main stimulant for central chemoreceptors is the hydrogen ion concentration. Okay, so as we can see, there is hydrogen ion concentration increase, but if this hydrogen ion concentration increases in the blood, it cannot stimulate this central chemoreceptors. Why? Because it will not be able to cross the blood-brain barrier, and it will not be able to cross the CSF. Okay, so it will act as a mild stimulator for this peripheral chemoreceptors. Okay, so here the effect will be very mild. Okay. Fine. So this is all about the chemical regulation. So in this way, we have covered both nervous and this chemical regulation part. Okay. So I hope you find this class helpful. And if you have any kind of doubt and query, so you can connect with us through these various platforms. Thank you so much.